to the lab owl. You go to the lab web page, you go to the left margin, you click on owl. If it tells you you're not rostered, you're not registered in this class, don't panic. You're registered in the class. But you're gonna be rostered after you do experiment 2. So if till now you didn't do experiment 2, you're gonna hit on owl, it's gonna tell you you're not rostered, you're not registered. Please don't go add yourself to owl, to the lab owl. Professor Whalen will take care of that after you do experiment 2. You know that the lab is every other week, so until you do that experiment 2, you would not be rostered by Professor Whalen. Okay? Now from chapter 4 on, which I'm gonna launch soon, the deadline is not gonna be the week after. But for chapter 4, we're gonna get started with the OWL book reading as required. So as you all seen that the OWL book reading, I put it as optional as a start. Now you're gonna read it and you're gonna begin doing some of the exercises, some of the tutorials in there, and those gonna be graded from chapter 4 on every time. And those are they are made by the OWL authors to help you understand the concept before coming to class, ahead of time. So prepare you to understand what I'm going to talk about in class. Now, if you have an exam time conflict and you figured out that it is the other professor, if you are in an engineering course, most probably the other professor is going to be the one who is supposed to give you a makeup exam, you need to talk to your instructor, to your other instructor. It's not me to communicate with him or her. You need to go to them ASAP with that registrar paper saying that he or she should or must give you the makeup exam. So the last time, now let's get started with chapter 4. So the last time we ended our lecture by doing the demo about conductivity, and we figured that NaCl aqueous in water, it conducts electricity, and this is why we saw the 5 lamps on. Then we did for sugar and no light. We did for acetic acid, which is vinegar, and it was 3 lamps on. And today we're going to talk what did happen, why is that the case, and we did FCL and verify on. Okay? So today we're going to talk about all of these details, how did this happen, and just as a reminder for you, an electrolyte is something that dissolves in water and conducts electricity. While a non-electrolyte, and we're going to say weak and strong electrolyte. A strong electrolyte is the electrolyte that caused the 5 lamps to be on. A weak electrolyte is acetic acid, 3 lamps on. The material or the matter like sugar, no light on, that's a non-electrolyte. So this is what we're going to talk about. Now let's say I have all of these 3 salts are water soluble. For the moment you don't know how to know which is soluble, which is not. This is what we're going to learn today using this handout. So make it ready, make it ready on your desk. So now I'm telling you for guarantee that those 3 salts are water soluble. Now when I add NaCl to the water, so NaCl solid, when I add it to the water, what happens, the Na is going to go to its ions, to the ions from which this ionic compound is formed. For example, here it's Na and Cl. How did I know that it's going to go to Na plus? Because I know that Na, first, this is an ionic compound that we learned how to determine whether it's ionic or non-ionic. Second, this belongs to group 1A, so most probably it's going to have a plus. Cl belongs to group 7A, that means it's going to have a -1, as it's going to be an anion and cation. So when I add ionic compound to water, it's going to go to its ions if it is water soluble. If it is water soluble. Now all of these are water soluble. Now barium chloride, again, it's water soluble. You know that this is group 2A and this is group 7A. So you know that this is going to have 2 plus, 1 minus. Now the thing that I see a lot in exams, that some of you would do. They're gonna write the equation as Ba2 plus Cl2 minus, thinking that this 2 means Cl2. Thus, this 2, which is in the ionic compound, should be now a stoichiometric coefficient, because that 2 is telling you for each one barium you have 2 Cl minus. And it is wrong to write it this way. When you write it this way, you're telling me there is a covalent bond between the 2 Cl's and all of the thing have a minus, which is not right. And I see that all the time, that most of the class choose something like that as a multiple choice, and that's wrong. So in other words, when you have barium chloride or any other ionic compound and it has kind of a subscript in here, the subscript gonna be a coefficient, a stoichiometric coefficient in the equation. Okay? So when I add barium chloride, it's gonna go to its ion, taking into consideration any subscript here or here. It depends. Now, the other thing that usually it's confusing for students is when I have NaNO3 or Na phosphate or sodium chlorate or chloride or sulfate, all of these. So the second thing that you're gonna face, if you have a monocation but a polyatomic anion. Now the polyatomic anion, for example, the NO3 minus, it's gonna go to NO3 minus. It's wrong. You can't say NaNO3 when you put it in water. It goes to sodium plus nitrogen and oxygen. I don't know what. This is what I see in exams, and that's wrong because this is a polyatomic anion. How are you gonna know that? You have to learn that. I already gave you the sheet which have the most popular polyanions. So when you saw those in an ionic compound, know that they're gonna go to the polyatomic anion, not to the elements there. Okay? Make sense? And you need to practice about those. Okay? How to go from how the ionic compounds, what are the ions of the ionic compound. Now, this is, we covered the ionic compounds. When they dissolve in water, they go to their ions, and all three of those, all these three are good electrolytes, are strong electrolytes, because they go into the water and they begin kind of transferring electrons if we apply voltage in the beaker. Now, molecular compounds, we said some molecular compounds are dissolves in water. One of them is HCl, which is a strong acid. When we add it to water, although HCl is a covalent, it has covalent bonding, because we said that H is the exception. When it have compounds H with any of 5A, 6A, 7A, 4A, it's going to make a covalent bond. So this is a covalent, it have a covalent bond. Although it have a covalent bond, when I add it to water, it's going to give me H3O plus Cl minus. Okay. Now, in other words, it's giving me H plus, it's going to its ions, H plus and Cl minus, but usually water, since we have water and we have H plus, they react with each other to form the hydronium ions, which I wrote in here. Hydronium ion. And that's the case every time I add an acid to water, we're gonna have the hydronium ion plus Cl minus. So in other words, it's the ions, but the H plus reacts with the water. Sometimes you would see it like HCl, it goes to H plus Cl minus. Both of those are right, but you have to know both of them. Now, as we saw that HCl is a good electrolyte, is a strong electrolyte. It calls the 5 lamps to me on, because it dissociates into ions, and those ions play the role of transferring the electrons inside the solution. Now, when we tried acetic acid in here, which is the vinegar, we added to water. What happens that not all of the acetic acid, only 1% of the acetic acid goes to its ions. The other wouldn't go. It would stay as acetic acid, as covalent bond. And this is why it is a weak electrolyte. Now, how are you going to know which is a strong acid, which is a weak acid, and all of these details? This is what we're going to talk about in the next slide. I'm going to show you how to know which is a weak acid, which is a strong acid. Usually, weak acids are weak electrolytes. Strong acids are strong electrolytes. Okay? If I'm you, I'll print out this table, or this is like, do you need one more minute? Guys, again, I have to remind you that the easiest way to handle the pace of this course, whether in my class and any other professor class, is to print out those presentations. Print it before coming here and uploading them exactly after the class, so that you will be able, you have time to print them and bring them here, so that you don't have to rush just running and concentrate on writing the material. Instead, you will be concentrating on what I'm talking about. So this is the table. That table, you should have it handy whenever you're doing strong electrolytes, or when we're gonna begin starting with the net ionic equation. This gives you a list of the common acids and bases, which one is a strong acid, which is a weak acid, and you need to learn this. You need to know that for the exam. I'm not gonna give you the list of strong acid and strong bases. So all of these are strong acids. And the acids that you need to know about, the weak acids that you need to know about, are those four. Now, strong acids are strong electrolytes. So all of these, when they are in water, they're gonna conduct electricity and they are good electrolytes. Those are weak electrolytes and they are weak acids. Now, I just wanna bring your attention that the acids of all halogens, all group 7, except F, are strong acids. All of these are strong acids. So HCl, it's a halogen, it's a strong acid. HBr, it is a halogen. It is from group 7A. It is a good acid. It is a strong acid. HA, it is a strong acid. Except HF, which is the first halogen in group 7A, it is a weak acid. Now, nitric acid, perchloric acid, and sulfuric acid are strong acids. Now, in addition to hydrofluoric acid, we have phosphoric acid, carbonic acid, and acetic acid are weak acids. Those are the ones that you need to know for this course. Now, I just want to bring your attention to how we name these acids. So, for example, if it have a chloride or a chlorine, we say hydrochloric acid. If it have a bromine, hydrobromic acid. Iodine, hydroiodic acid. Fluorine, hydrofluoric acid. So if it is one of the halogens, we're going to say hydrofluoric, hydroiodic acid. Now when it comes to, if we look to the HNO3, it's mainly coming from the nitrate ion. This is why we call it nitric acid. For example, see this H or H2SO4, it's coming from SO4 2 minus, which we know as sulfate. This is why it's called sulfuric acid. H3PO4, it's coming from the polyanion that we know, phosphate, and this is why it is called phosphoric acid. Okay? This is how, and the last one, H3CO2H, it's coming from the acetate ion. This is why it is acetate. This is why it is called acetic acid. You need to know the name. You need to know which one is strong, which is weak acid. You're going to be asked about in the exam. You're going to need it for later on when you're doing acid-base reaction. So in other words, if I ask you about any of the strong acids, they are by default strong electrolytes. If I ask you about the weak acids, by default they are weak electrolytes. Now let's go to bases. We have, those are strong bases. So almost everything that have an OH there with an anion, with a metal cation, it is a strong base. But the only thing about all of these, whenever they have OH, some of them are not water soluble. So they are strong base, but they aren't water soluble. They don't dissolve totally in water. There is a small part of them that dissolves in water. So all of these are strong bases, and this is why we didn't conclude here that they are strong electrolytes, because that depends whether they dissolve in water or not. And this is, we're gonna learn how to know whether they dissolve in water or not in a minute. Okay, so those bases that have OH and they dissolve in water, they are strong electrolytes. Now, the only weak base that we're going to talk about in this course is ammonia and H3, and it is a weak electrolyte. Okay, so you need to know all of these and learn it. Now, let's do an eye clicking. Definitely use the table that
close. Is there?
and I'm going to stop it at 1 minute. Which of the following is a strong electrolyte? I'm not asking if it is electrolyte or not. I'm asking if it is a strong electrolyte. Okay, so let's see what is the most popular answer for this question. So I have 86% for B. B is the right answer. Okay, let's see how. So sugar solution, it is, first of all, sugar is a covalent compound and it doesn't dissociate in water. This is why it is a non-electrolyte. And we did the demonstration and it showed that sugar doesn't turn on the labs. NaCl solution, we just learned that NaCl dissolves in water. It's the table salt that we eat. So it dissolves totally in water to give Na plus Cl minus. And those will help conduct the electricity. So yes, it is a strong electrolyte. HCl, it's hydrochloric acid. It is a strong acid. By default, strong acids are strong electrolytes. Now, acetic acid, if you go back to the table, which is vinegar, which is this guy in here, acetic acid is a weak acid. Weak acids are weak electrolytes. And I'm asking about strong electrolytes. So 2 and 3 are the right answer. That's make B is the right answer. Okay? Now we're going to learn about the solubility of compounds in water. What is soluble in water? What is not soluble in water according to Ionic? Those ionic compounds, which one will dissolve in water, which not? So you need this table. And what I'm going to do is simply walk you through how to read this table. So I figured out that some of you don't know how to use this table. So I'm going to walk you how to use this table. And this table will be given to you in the exam. You don't need to memorize anything in here. All what you need to know to do is to learn how to use it. So it gives you the solubility rules for ionic compounds in water. The first part of the table is going to tell us about soluble ionic compounds. The second one is what is not soluble. Not soluble. This is the soluble compounds. Okay, so I'm going to start with the upper part of this table. And let me put this down. Okay, solubility rules for some ionic compounds. First of all sodium or potassium or ammonium salts are soluble. What does that mean? If I say NaCl, it is soluble. NaBr, Na with any anion, it is water soluble. Potassium with any anion, it doesn't matter. KNO3, KBr, let's say potassium fluoride, all of these, all potassiums are soluble by default. Ammoniums, all ammonium compounds, ammonium nitrate, ammonium fluoride, ammonium bromide, ammonium iodide, all of these are soluble. This is what this is telling you. Okay? So this is the first rule. The second rule, all nitrates, acetate, chlorate, and perchlorate salts are soluble. And that means any salt that has this anion, which is nitrate, like calcium nitrate, it is water soluble. Barium nitrate, it is water soluble. Acetate, barium acetate, it is water soluble. Potassium acetate, it is water soluble. With any cation, let's say silver nitrate, it is water soluble, even if it is one of the cation is a transition metal. The same for chlorate, the same for perchlorate. Okay? Now, rule number 3. It tells you all chlorides and the bromides and iodide salt are soluble except lead the chloride, lead the bromide, and lead iodide are not soluble. This is what rule number 3 is telling you. Anything with chloride, bromide, iodide is soluble except if it is lead chloride, lead bromide, lead iodide, or if it is Ag with silver. Ag chloride, Ag bromide, Ag iodide. That wouldn't be soluble. Now, this one, forget about it. I'm not going to ask about it in this course. The mercury one, forget about it. So this is rule number 3. Rule number 4, it tells you that all sulfate salts are soluble except those that contain, okay, I think I put those in a better way. Okay, so for this one, so all sulfate salts are soluble except those that contains calcium. So calcium sulfate is not soluble. Ag sulfate is not soluble. You can ignore the mercury one. Barium sulfate is soluble, is insoluble, and lead sulfate is insoluble. So in other words, those ions with this, those cations with this anions will be insoluble. This is how we read this table. Does that make sense? Okay, let's do a trial. Let's see. Let's do an eye check. So the table will be given to you, so use the table. So which of the following is soluble in water? I'm going to put it at 1. You can talk to each other, talk to your friends, help each other figure it out. Okay, let's see what is the most common answer. I have C as 95% great. So 95% is a very good percentage. So NaCl, we go back to the table. All sodiums are soluble. So sodium chloride definitely soluble. Potassium nitrate, it says rule number 1, all potassiums are soluble no matter what is the anion. So this is soluble. Ag chloride, that goes back. I don't have a rule about silver, but I have a rule about the anion, which is chloride. And it says all chlorides are soluble except if they are lead or Ag or silver. So this is insoluble. Number 4, ammonium. I have a rule about ammonium, which is which is number 1. It says all ammoniums are soluble. Lead. I don't have a rule about lead, but yet I have a rule about chloride. So all chlorides are soluble except if they are with lead, so it is insoluble. Na, everything with Na is soluble. And that ends up with number C as the right choice. Okay, now the other half of the table. We're gonna walk you through the other half of the table. Okay, now it is, all of these are not soluble except if they are with something else. Now, rule number 5, hydroxide, oxides are not soluble. All compounds with hydroxide or oxide as anion are not soluble except those with sodium, potassium, and barium. And that goes back to rule number 1 because we said that sodium with anything will be soluble. And that kind of definitely would not contradict with rule number 1. So all hydroxides are insoluble except the soluble are sodium hydroxide, potassium hydroxide, and barium hydroxide are the only soluble from all the hydroxides that are out there. Okay? The same for the oxides. All the oxides are insoluble except those with sodium, potassium, barium. Now, rule number 6, it states that sulfides or sulfides are insoluble, not soluble, except those with sodium, potassium, ammonium, and barium. So the only soluble sulfides are sodium sulfide, potassium sulfide, ammonium, and barium sulfide. All the others out there are insoluble. Now, the last rule, it states that carbonate and phosphate salts are not soluble also. The only soluble are those with sodium, potassium, and ammonium. These are the soluble ones. Okay? Now, let's do a trial to make sure that everybody gets the idea in here. So, which of the following is insoluble, not soluble? And I'm going to stop it at 120.
Just have them marked on the board.
Where about this one?
No, I see. I see it.
Why is
Because Y is 3. The PO4 is a
okay? I
phosphate.
didn't see. Okay, I didn't see the phosphate at the same time. So yeah, 7.
That's smart with the rules.
NaOH soluble. It breaks for 5.
You could even narrate this yourself, roll it.
If I want, I'm good. Then. Just kind of got that down.
Yeah.
6.
Okay.
We're gonna lose this.
So the part here. So I have B as 89%. B is the right answer. Okay, let's start with barium hydroxide. I don't have a rule about barium, but I have a rule about the OH, which is hydroxide. It says all hydroxide are not soluble except if it is with barium, or sodium, or potassium. So this is soluble. Copper carbonate. I have no rule about copper, yet I have about carbonate, which is rule number 7. It says all carbonates are insoluble except if they are sodium with sodium, potassium, or ammonium, which is not the case here. It is with copper, so this is insoluble. Calcium phosphate. I don't have a rule about calciums, but I have about phosphate, and it is rule number 7. And says all phosphates are insoluble except if they are with sodium, potassium, ammonium. That makes this insoluble. NaOH, I know that everything with Na is soluble. This is rule number 1. calcium sulfide. Now, I have for sulfides, all sulfides are insoluble except if they are sodium, potassium, ammonium, or barium. So this is insoluble. So the right answer is B. Okay? So this kind of exercise later on during this lecture and the lecture after that, it should take you 1 minute or less to solve it because it's going to be within a much bigger kind of problem that we're going to solve, which is the net ionic equation. Now, let's get to start. We're doing all of this to start with the chemical reaction in solution, and one of them is the precipitation reaction. So what is a precipitation reaction? Mainly a precipitation reaction, I'm going to have an aqueous solution, like something like two solutions like this, either transparent or they look homogeneous as a mixture. I'm going to add them to each other, and guess what? I'm going to get a precipitate. This is what a precipitate reaction is. I'm going to add two aqueous solutions. That means both of these solutions, they're going to have a salt, and the salt should be one of the soluble salt. It couldn't be one of the insoluble salt. So I'm going to add a soluble salt to a soluble salt and get something which is a precipitate. And the precipitate, that means it's a solid in the bottom of the beaker. Something like that. We didn't check. Okay, so something like this, okay? Now I'm going to turn on that. The document camera for J. You may need to zoom in or somehow. Okay? So, what is the generic formula or the generic reaction of a precipitate reaction? First of all, we're going to have AB, which is, for example, NaCl. Let's say, that's an example of that. That means a cation plus anion, a cation plus anion. And what's going to happen, that A going to swap its anion with the other compound. That means instead of being AB, it's going to be AD. It's going to take the anion of the other compound. So I start with AB plus CD. I'm going to end up with AD plus CB. Okay? So always happen that the D going to come here and the B going to go there. And from there, I'm going to look to the solubility of AD and CB in these tables and figure out which is the precipitate. Does it form a precipitate? If it does form an insoluble, if one of these is insoluble, that means this is a precipitation reaction. Because the whole idea of a precipitation reaction is that I start with two soluble stuff and then end up with something which is insoluble. Okay? Let's start with an example. An example of that, which is Jay can show us, is we have Ag and O3. We can okay, so okay, so we have two solutions in here. As you can see, both of them is colorless. One is Ag nitrate, silver nitrate. The other is KCl, potassium chloride. And Jake gonna add one to the other. And as you can see, it's get turbid there. It's get kind of milky. And it is yellow in color. And this is how it looks. Okay? Which means that it's formed a precipitate that if you leave it for 1 day, it's gonna be transparent. This solution gonna be transparent, and down there we're gonna have a precipitate. Okay, let's figure out what is this precipitate. So I have AgNO3, KCl. As I said, the anions will be swapped. That means this Cl gonna go to the Ag, this nitrate gonna go with the K, and I'm gonna end up with Ag chloride plus NaNO3. Now I'm gonna figure out which is soluble, which is not. Ag chloride. I'm gonna go to the table. I don't have a rule about silver or Ag. But I have a rule about chlorides. It says that all chlorides are soluble except if they are with Ag. So this is insoluble. And this is the precipitate that I'm seeing. This is the yellow precipitate you're seeing. While NaNO3 is water soluble because all sodium compounds or sodium ionic compounds are water soluble. And this is rule number 1. So I figured out that the water precipitated is Ag chloride. Yeah. And that's right, yeah. It's either here potassium or here sodium. Yes, it is potassium chloride plus Ag nitrate, that's for sure. Okay. So this is what is a precipitate reaction. This is what we're gonna do now. Okay? This is the main reaction. Yet, what we're gonna look for is what we call the net ionic equation. That means what did take place as a reaction. So what we're gonna talk about is spectator ions. Spectator ions, think about it as there is the football game. There are audience in the stadium. The audience are just encouraging and watching the football game. They aren't the real player, but they are part of the whole thing. But they aren't the player. They aren't the football player. Those audience that they are just looking at the football game, they are called the spectator ions. They are there, but they don't do a reaction. They are just there. Spectator ions. Now, in this case, in this reaction, the spectator ions are there just to balance the charge, to make pluses and minuses equal inside the solution, but they aren't doing a reaction. Now, how we figure the net ionic equation? To figure out the net ionic equation, we have a couple of steps. The first step is to write the main reaction, which is AgNO3 aqueous plus KCl aqueous to give Ag chloride solid plus potassium nitrate aqueous. Now, as we said a minute ago, or 4 kind of slides ago, we said that Ag nitrate is water soluble. So when I'm going to put it in the solution, it's going to go to its ions, which is Ag plus NO3 minus. Why? Because it's water soluble, and we said that all water soluble stuff, when I put it in water, it goes to its ions. Same for KCl, it is aqueous, it is water soluble. I figured that from the table. So it's going to go to its ion, which is K plus Cl minus. Now, Ag chloride is insoluble in water. So it's going to be as a precipitate, as a solid, as you saw. It's going to be on the bottom. It's not going to dissolve in the solution. It's going to stay as Ag chloride. It wouldn't go to its ion. While KNO3 is water soluble, so it's going to go to its ion. Now I'm going to begin looking what exactly which of these ions and cations are involved in the reaction and which were there just as spectator ions. Now I'm going to look at the potassium. The potassium in the reaction is potassium aqueous, that means an ion. After the reaction, it's still potassium aqueous. So it didn't change. It didn't change from potassium, for example, to a solid that is precipitated. So we call potassium a spectator ion. Because it didn't change before and after the reaction. Now I'm going to look at the nitrate. The nitrate before the reaction, it is NO3 minus. And after the reaction, it's still NO3 minus aqueous. So we're looking to the anion, and that it is aqueous before and after. It's not solid, so it is also a spectator ion. Now whatever left, like Ag plus, it was Ag plus aqueous. Now it is Ag in an insoluble compound. So it changed from an ion moving inside the beaker to an Ag inside an Ag chloride and precipitated in the bottom of the flask or the beaker. So Ag is not a spectator ion. It's the cation or anion that interacting, that doing the reaction. Cl minus, it was Cl minus aqueous. Now it is in a compound, it's in an ionic compound that is solid. So those, the ones with the red kind of brackets under them, those that undergo the reaction. And those two are spectator ions. Now the net ionic equation is Ag plus Cl minus aqueous to give Ag chloride solid. So in other words, it's after I cancel those, because those are our spectator ion, whatever left in that equation is the net ionic equation, and we're going to refer to it as NIE. In exams, I'm going to ask you, write the net ionic equation of this reaction. Make sense? Any questions? Okay, so let's go do more examples, okay? Let's do an application. So I have copper sulfate plus sodium carbonate. What is the precipitate? And try to write the net ionic equation. Start writing the net ionic equation. Figure out what are the spectator ions.
CO2 is the soluble. They're not soluble. That's what in that solution.
I'm going to stop it at 1. Okay, so I'm going to stop it at right here. And check. So I have C as the most popular answer. First of all, let's see if there's going to be a precipitate or not. So we have both. The copper sulfate is the blue solution in there, because usually copper 2 plus have always the blue color. And the other one is the sodium carbonate. So taken as a each other. And maybe we already prepared some last night so that you can see the precipitate, because it takes time for the precipitate to settle. And as you can see, this is how it's going to look after a day. After a night, it's all going to, the copper carbonate that is formed, that you guess that it's going to form, it's going to be down. So, first of all, we're going to swap an ion, but the only different thing about this example is the following. So I'm going to swap an ion, so copper is going to be with copper carbonate, and sodium is going to be with the sulfate. And I'm going to stop for a minute in here. So copper has a 2 plus as a charge, and carbonate a 2 minus. So this is balanced. This compound is balanced. For this one, we have sulfate 2 minus, and sodium is 1 plus. So it isn't balanced. We need to balance it. And to balance it, you need to put 2 there. And this is your next step whenever you're doing a precipitate reaction. Make sure that whatever you're writing is balanced as an ionic compound. So we go back to the rule. Copper carbonate is solid, it's insoluble, so it is the precipitate. Sodium sulfate is water soluble, so it is aqueous. Now our next step is to write the net ionic equation. but we don't have time, so we're gonna do the left ionic equation on Friday.